we are starting on our last resource of our resources unit, which is exciting. Um, so we are going to talk about the atmosphere. I know we talked about the atmosphere when we learned about Earth's spheres, um, way, way, way back in the year. But today we are talking a little bit more in depth about the Earth's atmosphere and a little bit of how the atmosphere is considered a resource in the first place. Tomorrow we will talk about air pollution. Wednesday we will talk about how we control air pollution. And then Friday we will have an activity to go along with it. Um, and then next week we've got a couple days of review, and then the test over all of this stuff. I don't do tests super duper often, um, but when I do, I want to make sure that you are prepared for them. So, make sure I have my stuff. Y'all have your notebooks out. That's phenomenal. Alrighty. So, my goal for today is for you to be able to describe the four main layers of the atmosphere, um, a little bit about what those layers do and how they interact. So, starting us off, what is the Earth's atmosphere? You just need what is in the blue. The black is just to remind me what to say. So, the atmosphere is the layer of gas that surrounds the Earth. Um, and if you were to, this was actually really cool. So, if the Earth was an apple, right? We've all heard if the Earth was an apple, then the Earth's crust would be as thin as the skin around the apple. Well, imagine if you had an apple right in front of you and you were just to like breathe on it really heavily, just like right, and that kind of creates a thin layer of condensation. That layer of water, in comparison to the apple, is how thick the atmosphere is. It is very, very, very thin in comparison to the entire globe. But when we think about how we have to launch people through the atmosphere to get them to space, it kind of puts into perspective like the Earth's really, really big. So that thin layer of gas is everything that we breathe in. It helps keep us warm, but it is also very, very easy to pollute. So to talk about the properties of the atmosphere, we can break it down into four main characteristics. The first of being composition. What's it made of? The different layers of the atmosphere have different things in them. Relative humidity, uh, which is how much water vapor is in the air. Temperature, obviously, how hot or cold it is, and then air pressure. Um, sorry. Whew. So, composition, humidity, temperature, and air pressure are the four big properties that we're going to talk about when it comes to how we describe the atmosphere. Doing okay? Okay, I didn't ask questions before we get started. All right. So, starting off with composition, um, you just need these first three really, really big bullet points. This is all pictures. So, um, when we think about the atmosphere and the air that we breathe, we normally think about oxygen. But in reality, the atmosphere is 78% nitrogen gas. So there is a lot more nitrogen in the atmosphere than there is oxygen. Um, Oxygen makes up about 21% of the atmosphere, and that last other 1% is a bunch of different gases, things like argon, carbon dioxide, neon, helium, methane, and water vapor is also considered to be in that 1%. So while there is a lot of water in the atmosphere, if you think about how much water is trapped in a cloud, that's a lot of water. That barely makes up, or that doesn't even kind of scratch the volume percentages that are given in the atmosphere. So there's a lot of stuff up there. And while in comparison to the Earth, it is relatively thin, um, it can hold a lot of stuff. Uh, so mostly nitrogen, uh, decent amount of oxygen, and everything else kind of makes up that 1%. Let's see. I'm trying to sing the periodic table in my head. I used to have a periodic table up here, and I've lost it. Yeah, I believe the argon, neon, helium, and krypton are all noble gases, which explains why they're in the atmosphere because they're stable by themselves. Um, so yeah, those are that is the composition of the atmosphere. When we talk about relative humidity, we are talking about the ratio of water vapor that is in the air related to the maximum amount that it could have at that temperature. So water or air can hold a lot of, air can hold different amounts of water based on how cold or hot it is. Warmer air can hold more water than colder air. Um, so in the summer, um, when you're outside and it is so humid you can barely breathe, and you turn on the weather channel and they say it is 98% humidity outside, that doesn't mean the air we breathe is 98% water. It means that of the amount of water that can be in the air, we're at 98%. Um, and why you might see a higher number of humidity outside right now, even though it's cold, um, but that it doesn't feel as wet in the air because cold air doesn't hold as much water as hot air does. So, relative humidity is the amount of water vapor in the air related to the maximum amount that could be in the air. Um, when water vapor is cooled, it will condense um, back into a liquid, and this is how we get clouds. Uh, but water can't just condense out of nowhere. Water has to condense on something. You've ever been sitting with a glass of water and then all that water is on the outside of your glass? Um, that that water has to have something to grab onto in order to condense. So if I had ice in this cup and the outside of this got all wet and condensed, it means that the coldness of my water bottle um, cooled the water in the air enough for it to condense into a liquid. Um, so that on a major scale is what happens in the atmosphere, but it has to have something to latch onto. So water will condense around tiny dust and dirt particles in the air. Um, so whenever it rains, raindrops and snowflakes aren't just water; they are water and all of the gunk that is up in the atmosphere. Um, it's actually really cool. If you were to take like rainwater or just like scoop up some snow from outside, let it melt, and look at it under a microscope, there's a lot more junk in there than you would have thought, which kind of makes the idea of snow ice cream a little less appealing, but it is what it is. So, relative humidity is the ratio of water vapor in the air related to the maximum amount that it could be. Air temperature, like I said, was another property of the atmosphere that differs within the levels. And it varies from place to place, specifically due to where and how the sun's rays strike the earth. So around the equator, it is a lot warmer than around the poles. That is because the equator gets closer to the sun than the poles do. And wherever the sun rays hit, the atmosphere can trap some of that heat and keep it there. So that is why we have seasons and temperature differentials between like up north and down south. As you can see, the Earth is tilted. Right now, we are tilted away from the sun, which is why it is winter, and so on and so forth. So temperature varies from place to place, but also with altitude. The higher up you get, the different the temperature is going to be. And lastly, air pressure. Air pressure is also called atmospheric pressure. And it is the force exerted by air on the area below it. Now, you might not think of air as having mass because it's just what we move through every day. But if you think about a helium balloon, right, that helium balloon is going to float up because it is less dense than the air around it. Air is also, if you ever take a physics class, air is considered a fluid. Fluid and liquid are completely different things when we're talking about physics. So if we think about something moving through a fluid, if we are moving through water, right? If you are in a pool and you swim down to the bottom, your ears feel like they're going to explode because down at the very, very bottom of the pool, you are under more pressure than you are up at the top of the pool. And the same thing goes with the atmosphere, right? Down here on Earth, we are feeling all of the pressure from all of the air in the atmosphere. But the higher you get, the thinner the air gets and the less air that is pressing down on you. It is why people who train for the Olympics in high altitudes and people who train for the Olympics in low altitudes have to figure out where they will be competing so they can adjust to how much air pressure they are used to with their training. A barometer is the tool used to measure air pressure. So these are mostly mechanized now, and much like the automatic thermometers that you put in your mouth are all computers and stuff. But there are more liquid and mercury barometers out there that essentially measure the force put onto the Earth by the air above it. This is important when it comes to meteorology, because if you think about the amount of water vapor in the air, right? The more water vapor in the air, the heavier the air is going to get. So the heavier the air gets, the more likely it is to rain because there is more water in the air. So in general, like I said, lower the altitude, the higher the air pressure because there is more air above you. Everybody doing okay? All right. So there are four main layers of the atmosphere. The troposphere, the stratosphere, the mesosphere, and the thermosphere. So the troposphere is everything from sea level up to about 10 kilometers. And then the stratosphere goes from that 10 mark to about 50 kilometers. We've got the mesosphere from 50 kilometers up to about 85, and the thermosphere up here at about 90 kilometers. So as you can see, airplanes tend to stick to the lower stratosphere, often not getting much higher than that. Weather balloons can make it up to the upper stratosphere in order to measure air pressure changes. And then when a comet falls, or not comet, a meteorite falls, usually the mesosphere is what burns it up, and that's where we get shooting stars. And then up here, the thermosphere. So we're going to go through each one of those, give it a little bit of context. Doing okay? All right, so the troposphere is what blankets the Earth's surface. It is the closest thing to us. It has all of the oxygen that we breathe, and it is largely responsible for weather. Um, so all of the clouds we see are in the upper troposphere. The troposphere has 3/4 of the Earth's mass, or not Earth's mass, the atmosphere's mass. Sorry, but much less space. As you can see in this picture right here, the troposphere doesn't get up very high, but that it has most of the atmosphere's mass. And that is because as we get higher into the atmosphere, the thinner the air gets, the less stuff is in it. All of that water vapor stays in that troposphere, which takes up a lot of space and a lot of weight. Um, so the troposphere is the closest layer to the Earth's surface. It has all of the oxygen that we breathe in it. It has the responsibility of the weather. Um, so whether or not it determines if it snows or if it rains or if it's sunny, that is all up to the troposphere and those conditions. Um, like I said, a lot of mass, not a lot of space. I'm trying to think of a metaphor. It's all about density. So if you think about like a one of those pumice stone rocks, right? They're a lot lighter than a like fully fledged out like piece of metal. So even though if they took up the exact same space, the metal would be a lot heavier, and that's the same thing with the gases in the atmosphere. There are heavier gases that take up a lot less space than the same mass of a lighter element. Um, because we can't really see it, it's a little wonky. But. So that's the troposphere. Moving on up into the stratosphere. Um, this is the layer above the troposphere. And gases don't mix much up here. Um, in fact, one of the big issues here is that when pollutants enter the stratosphere, they don't move a lot. If wind is down in the troposphere, the stratosphere doesn't experience a lot of disturbances. So when pollutants get there, they stay there. It's really hard to get pollutants out of the stratosphere. Um, this is also where the ozone layer is. Now, a lot of people, it's without knowing a lot about the ozone layer, some might think that ozone is a bad thing since it is considered a greenhouse gas. But ozone or O3 gas is like sunscreen for the Earth. So the sun uh, gives off radiation, and ozone, that ozone layer, will protect the Earth from from the radiation of the sun. Now, if you've heard talk of like the hole in the ozone layer, it wasn't necessarily a hole, but the layers of ozone above the poles of the Earth were getting a lot thinner. There was a lot less ozone up there for a while, which let in more radiation. And as we know, radiation is a carcinogen and can cause a lot of damage. Um, we found out that there were special gases called chlorofluorocarbons or CFCs that, when released into the atmosphere, interact with ozone and kind of turn it into something else, which takes ozone out of the ozone layer. When we realized this, we were able to kind of combat it. And the hole in the ozone isn't necessarily a big deal anymore. We've pretty much got it under control. Or at least it's not getting worse at the rate that it was getting worse back in the 60s, 70s, and 80s. Or maybe 90s and early 2000s. My timeline's a little bit off. But there are much bigger issues now with the atmosphere. But ozone was one of the first, like, oh, our actions affect the atmosphere. Maybe we should like pay attention to the composition of the atmosphere, kind of things. So that is the stratosphere. Let's see. Oh yeah. This is what ozone looks like, just as a like this is a molecule of oxygen. This is a molecule of oxygen. This is a molecule of oxygen. The oxygen we breathe, the oxygen gas that we breathe, is just two of these. So usually they exist with two little oxygen molecules, but ozone is three. Moving on up to the mesosphere. It is, like I said, above the stratosphere. And this is where meteorites burn up as they travel through. So we don't have as much information on the mesosphere as we do the stratosphere, at least for our purposes. But the mesosphere is dense enough that when meteorites move through it, they will break up, and that is where we get our pretty shooting stars. So while we might think that we can see where they came down to go try to find them, usually they burn up before they even get to the stratosphere. So it looks a lot closer than it is. And we got one more, and that is the thermosphere. The thermosphere is the top layer of the atmosphere, and up here the air is very, very, very thin. So thin, in fact, that any disturbance to that layer is what creates the northern lights, or the aurora borealis. So it is interactions between gases and lights way up there that we see these. So that is the thermosphere. When we think about the northern lights, they look a lot closer than they are, obviously. When you think about where the thermosphere it is way, way up there, like almost, I think almost 1,000, yeah, almost 100,000, yeah, almost 100,000 miles or kilometers, sorry, up. So when we think about the northern lights, they are very, very, very big. So that is the thermosphere. Any questions about the layers of the atmosphere? All right. So, weather. I want to talk quickly about heat in the atmosphere. So, energy from the sun heats up the atmosphere. That is where we get all of the energy on Earth, is from the sun. So, as energy from the sun heats up the atmosphere, it drives, not dries, air movements and influences weather and climate patterns. So, like I said, this all happens in the troposphere, which is that, or troposphere, yeah, which is that first level. So, when the sun goes through all of those layers of the atmosphere, it makes it through the ozone layer. Where the heat is will influence where the air goes. So, mini chemistry lesson, right? The hotter something is, the more energy it has. So the hotter air is, the faster those gases are moving. And the faster those gases are moving, the bigger effect, I guess, that the atmosphere in that particular area will see. And when hot air and cold air interact, that's where we get our more interesting weather patterns, which I will talk about in the next slide. But heat interacting in the troposphere is pretty important. So, when we talk about heat in the troposphere, there are different ways heat can interact, and those are radiation, conduction, and convection. All of these happen in the troposphere, but we could also think about them in ways that we interact with them in everyday life. So, radiation is the transfer of energy through space. So, if we were all sitting around a campfire, right, you stick out your hands, they feel warm. That is heat transfer by radiation. So, if you had those little hand warmers, you set them on the table, put your hand over it, not necessarily touching it, that would be considered radiation. Uh, yes. Conduction is the transfer of heat directly between two objects. So if you're heating up something on the stove and before it gets too hot, you put your hand on it, right, just to see if it's working. That would be considered conduction. It is also how your pan heats up when you set it on the stove, right? The pan, the metal gets hot, just like the actual stove gets hot. That is heat transfer by conduction. And finally, we have convection, which is the transfer of heat by the movement of currents within a fluid. Like I said, fluid can be air or a liquid. So when we talked about the formation of tornadoes, right, when we talked about our natural disasters unit, we talked about how warm air was moving up and cold air was moving down, and warm air was moving up and cold air was moving down. That kind of circle is convection. So whenever you have a convection oven, right? If an oven is marketed as a convection oven, it often means that there are fans in that oven that will circulate the air so that stuff on the bottom rack doesn't get hotter than stuff on the top rack. Yes. Those are the three types of heat transfer. And just like they happen with us and the things that we do on a daily basis, they can also happen within the atmosphere. So, finally, air masses and air fronts. So, if you've ever watched the weather and you've heard someone say there is a cold front moving this way or a warm front moving this way, this is what they're talking about. A large body of air is called an air mass, and that air mass has similar pressures, temperatures, and humidity. The boundary between two air masses, that is called an air front. So, if there was a big a big segment of air in the troposphere that was super warm and super moist, and that big section of warm, moist air was pressed right up against an area of cool, dry air, that kind of line between the two where they start mixing, that is called a front. And if the warm part is moving toward you, that is called a warm front. And if the cold part of it is moving toward you, that is called a cold front. So it's just where those air masses combine. And it's not all just temperature and pressure. I mean, a lot of it is temperature and pressure, but humidity, like I said, has a big role in it as well. Mostly because, like I said, the hotter the air, the more water it can hold. So, questions here. This is the atmosphere. This is the baseline for what we talk about when we're talking about air pollution and the effects air pollution has, and what we are trying to control with governmental regulations on what can be emitted into the atmosphere and what cannot be. So, I'll let you get this down. There's an exit ticket on Canvas. If you could fill that out for me, please. That will set us up for tomorrow when we start talking about air pollution. So, if you could knock those out for me, please, and thank you. We are all set.